Before we go on any further, I would like to highlight one particular property of the wave, and that is the phase of the wave. Well, we're mostly interested in phase difference, but let's see what this is. When a wave propagates in a medium, say this is a wave traveling in a medium, this is the leading edge of the wave. That is, the particles this side are yet to be disturbed. Particles here are in various states of vibration. Sorry about the way I have drawn this wave. Freehand drawing sometimes will result in something like this. Now, well, different particles are in different states of vibration, and this particle is just about to get disturbed. So let's say it's phase 0. Phase is a term which refers to the state of vibration. Now what does that mean? Well, how do you refer to state of vibration of a vibrating particle? Now, to refer to any state, you must refer to the quantities that change as it changes state. So here we have vibrating particles. These particles are in simple harmonic motion, and well, their velocity, acceleration and position change. But if you know this phase angle, like let's go back to the equation for an oscillation, say x equals xm sine omega t. If you know the angle part of this function, trigonometric function, you will know x, and if you know x, you know v also. I'll differentiate this, you will get again you have same omega t, omega xm cos omega t. So if you know this angle, well, you know position, you know velocity, and you know acceleration. Differentiate this and you'll get, well, minus omega squared xm sine omega t, or this will be minus omega squared x. This you have learnt in simple harmonic motion. So if you know this angle, well, you know the position, you know the velocity and the acceleration of the particle in simple harmonic motion. So this is the phase, right? The angle part of the trigonometric function that represents the oscillation, that's the phase. Let's arbitrarily choose the phase of this as 0, and one wavelength away, this completed one oscillation. Phase goes up by 2 pi for every oscillation, so the phase of this particle is 2 pi, and this is one more oscillation, so this is 4 pi. So this particle is just about to begin vibrating. This completed one oscillation and this completed 2 oscillations. This is a picture at a set moment of time. Different particles are in different states of vibration, and this phase varies continuously. What do you mean by that? Well, this particle's phase would be, well, this is pi by 2. Is there a particle with a phase pi by 4? Yeah, find somewhere here. That is, as you travel away from the source, phase decreases. It decreases by 2 pi for every wavelength you travel. So if you travel distance L along the line of propagation, the phase changes by, say, or let's call that delta x. If you travel a delta x along the line of propagation of the wave, the phase changes by this much. So phase difference between two particles at distance of x1 and x2 from the source would be this. For every lambda, phase changes by 2 pi. In fact, a nice way of putting this would be phase decreases by 2 pi for every lambda you travel. Phase decreases continuously by 2 pi for every lambda you travel along the line of propagation. Seems a very simple thing to learn, but you would find you need to be clear about this. As you go away from the source, phase decreases. Phase decreases continuously, and it decreases by 2 pi for every lambda you travel away from the source. That's it.